Welcome back, and we are going to continue our discussion on the biomechanics of the bone. Previous session we had discussed the biomechanics of the bone, and we discussed about the structure of the bone, where we saw that there is a collagen and hydroxyapatite. Then we saw about the cells of the bone, and then we went on to two type of bone, cortical and cancellous, and a brief introduction about the why do we need to study the mechanical properties of the bone. And here we focus on the mechanical properties of the bone, which are anisotropicity. Second one is the strength of the bone. Third one is the fracture toughness of the bone, and fourth one is the strain rate of the bone. Right? Let us discuss. Yes, the first property of the bone is its anisotropic nature. In our high school sessions, we used to study about isotropic materials and anisotropic materials. Isotropic means they had some same quality, same properties. Anisotropic means they had some different properties, and that is the same here with the bond. Anisotropicity of the bond means that the properties of the bond or the character of behavior of the bond will be different in different direction of force applied. More clearly, the properties of the bond will be different in different direction of the force applied. For example, you have a bone tissue over here, right? You have a bone over here, and you apply a force in this direction. This is the longitudinal force. The property exhibited to this longitudinal force will be different from the property exhibited to this transverse force. That is the anisotropicity. That means the properties, the mechanical properties of the bond will be different according to the direction of the force applied. When force is applied in longitudinal direction, that property will be different from the force applied in the transverse direction. That is the first unique property of the bond. That is the anisotropic nature of the bond. Now, in human bone, there is a slight difference. That means even though our bone is anisotropic in nature, we can call our bone anisotropic in nature, we also call it transversely orthotropic, or isotropic. That means the longitudinal force or the character exhibited to the longitudinal force is going to be different from the character exhibited from the transverse force. But a transverse force applied from this direction, that is lateral to the median, or from this direction onto the bone, is not going to produce different characters. That means in transverse direction, whatever the direction of the transverse force, that is from the right side to the left or left side to the right, the property that the bone is going to exhibit to that force will be same. That is why we call a bone as transversely orthotropic or isotropic. Transversely isotropic. It is anisotropic in nature, but the bone is transversely isotropic. So if we summarize, we call the property like this. Our human bone is anisotropic in nature. That means the human bone is going to exhibit different mechanical properties to the force according to the direction of the force applied. When the direction of the force is longitudinal, the property exhibited is going to be different from the direction of the force when it is transverse. But there is an exception. Regardless of the direction of force in the transverse direction, regardless of the side of the force from which it comes in the transverse direction, the properties of bond that it exhibits is same. So we call transversely orthotropic or transversely isotropic. Now, when we discuss about this isotropicity and anisotropicity, we have two constant values which denote these properties, and we have to define that constant values. and that constant value or that mechanical property of the bond which is related to anisotropicity are these two characters, that is the Young's modulus, which you would have studied in your biomechanics chapter. Stress strain curve, you would have studied it, law deformation curve, and second one, it is the Poisson's ratio. This you may not be familiar with this, right? So Young's modulus of elasticity or modulus of elasticity E is defined by the formula. What is the formula? Change in stress by change in strain, that is delta stress by change in strain. Stress is, you know, that it is force by area. Strain is, you know, that it is L2 minus L1. Okay, and it is new length minus old length. So what do you mean by Young's modulus? Young's modulus of elasticity is a constant value which denotes the change in stress of a bond divided by a change in strain of the bond. And change in stress is defined by F by A, force by area, and strain is defined as old length minus new length minus old length, or change in the length. Need not worry about the formula, just remember the formula for your career or your academics. What is important is you need to find out the Young's modulus value of the bond, right? You need to find out the Young's modulus value of the bond. When we examine the cortical bond, we see that it has a Young's modulus of 17 to 27 GPa, that is gigapascal. Whereas your cancellous bond has a Young's modulus of 2 to 20 GPa. 2 to 20 GPa. How do you relate this to a real life scenario? For example, in a steel that we have, the steel, it has a GPa of 200 gigapascal. See the difference? The bond is having only 70 to 22, 27. This is having 200. The titanium alloy that we use in our bone graft and in joint replacements is having a GPa of 115 GPa. See how lesser is the Young's modulus value of the bond? The Young's modulus value of the bond is 17 to 27 GPa, and the steel it is 200 GPa, whereas titanium it is 115 GPa. Right? There is a value difference between cortical and cancellous bond. The cortical bond in this would be in the longitudinal direction. This is in the transverse direction. So if we summarize, we know that Young's modulus is change in stress by change in strain, which is force by area divided by L2 minus L1, and you get the Young's modulus. And if we take an example in cortical bond in the longitudinal direction, it is 17 to 27 GPa. In the transverse direction, it is 2 to 20 GPa. I told this as a cancellous bond. I was sorry about that. That is actually the transverse value. The transverse direction, it is 2 to 20 GPa. Whereas to compare it in real life scenario, take the example of steel, it is 200 GPa. Take the example of titanium alloy that we use in our bond graft, it is 115 GPa. So such a great difference between bond value and the real life scenario objects. Okay, and of course there is a difference between the cortical and cancellous bond. The GPa, the Young's modulus value of cortical and cancellous bond is going to have a great difference. But we were not going to focus upon that. We just need only this much for our theoretical point of view. And now we are moving on to the next property of the bond, that is the strength of the bond. Okay, that is the strength of the bond. The strength of the bond, second property, that is strength of bond. All right, what do you mean by strength of the bond? The ultimate strength of the bond, you cannot define it. You might think that strength, we know that what is the strength of the bond, but you cannot have a constant value for the strength of the bond, ultimate strength of the bond. It differs with the type of the test that we use and type of the bond on which we test. So that is the difference in ultimate strength value of the bond. Okay. For example, the ultimate strength of the bond differs between the direction of the force. When there is a transverse force or tensile force, and when there is a compressive force, the strength of the bond is going to have a variation. In tensile force, the strength of the bond is having a less strength, whereas against compressive force, the bond is having a greater strength. That is what we discussed earlier in the biomechanics of bond, that bond is capable to resist compressive force. So when there is a compressive force, the ultimate strength or the strength of the bond is high. Against a compressive force, the ultimate strength of the bond is high, whereas against a tensile load, the strength of the bond is less. Tensile load, the ultimate strength of the bond has a value about 100 to 150 GPa. 100 to 150 GPa, whereas against a compressive load, the force or the ultimate strength of the bond is actually about 130 to 230 GPa. 130 to 230 GPa. See the difference? Against the compressive force, bond is having greater ultimate strength, whereas against tensile force, bond is having lesser ultimate strength or strength. Whereas for the steel, it is about 400 GPa. See the difference? The steel, it is 400 GPa. The steel, it is 400 GPa. So ultimate strength of the bond is the strength of the bond or the ability of the bond to resist compressive and tensile loading. This ultimate strength of the bond do not have a constant value. It differs between the type of the bond and amount of the type of the test that we perform. In general, the tensile nature of the bond or against the tensile force, bond is having lesser ultimate strength as compared to that of the compressive load. Or more clearly, when the load is compressive in nature, the strength of the bond is higher. When the load is tensile in nature, the strength that the bond withstand is lesser. And for instance, in tensile load, this is 100 to 150 GPa, whereas in compressive load, it is 130 to 230 GPa. Right? And next property of the bond is fracture toughness. The next property of the bond is fracture toughness. Right? And what do you mean by fracture toughness? Fracture toughness is a value which shows that the bond which is having a crack is able to resist that crack. The ability of an object to resist the already made crack is known as fracture toughness. So fracture toughness means it is an ability of an object to resist a crack that has been already made. It is not to resist a force, it is not to resist a fracture, but it is about not to resist a crack which there is already a crack made inside the bond. The bond is not able and the bond has an ability to resist that crack from developing. That property of the bond is known as fracture toughness. Okay, so the property of the bond which resist or which help in resisting the crack, further crack, is known as fracture toughness. And of course, we don't have a constant value, we don't have a consistent value for fracture toughness of the bond. We don't have a consistent value for the fracture toughness of bond. And of course, we take up a consistent value for the fracture toughness of bond. That value is actually 3.3 to 6.4 megapascal per meter square. It is actually 3.3 to 6.4 megapascal per meter square. Right? That is the fracture toughness of the bond. How can you relate it to the real life scenario? For example, the ceramic that we have, the ceramic that we use is having a fracture toughness of only 1.5. Is having a fracture toughness of only 1.5. Whereas the PMMA, which is polymethyl acrylate, this is actually used in our bond cements. Okay, this is also having a value of 1.5 to 1.7. See, when you use additional substance instead of the bond or artificial substance for the bond to replace that bond, the bond is actually having this property in a higher amount. That means the fracture toughness of our natural bond is higher than synthetic or cosmetic or what do you call the artificial ones that we use, that is 3.3 to 6.4 megapascal per meter square. Whereas in steel, it has 70. Steel has about 70. So steel is always an extensive one. It always has a greater value. But when we compare with the natural substance and the artificial ones, of course, the bond is having greater fracture toughness, and that is advantageous to us. So that is the third property of the bond, which is the fracture toughness. And here there is a difference. The cortical bond has lesser fracture toughness. Why? Because you know that the cortical bond is harder. It is a stronger one, it's a hard one, and there is no trabecular system which can withstand a greater amount of strain and stress. So this bond is having less capability of a fracture toughness. So if you have a fracture, there is a greater chance of breaking when it is in the cortical bond, because it is brittle in nature. Right? So the cortical bond has fracture toughness less than that of the cancellous bond. And the next property, which is the last property of the bond, that is the strain rate sensitivity. What do you mean by that? Strain rate sensitivity. Strain rate sensitivity or strain rate. This is actually a viscoelastic property. You might have studied in your biomechanics chapter viscoelastic nature of the connective tissue. So here that comes this one, what is this? The strain rate. What do you mean by that? This is, your bond is going to behave in a particular manner when it is loaded slowly, and the bond is going to behave in another particular manner when it is having fast loading. That means when the loading of the bond changes between slow loading and fast loading, the property of the bond changes. The bond is able to withstand a greater amount of force when the loading is faster. And when loading is slow, the ability of the bond to withstand, or the growth or hypertrophy of the bond to that force, is less. That means human bones are designed in such a way that they are having better ability to withstand which type of force? Fast loading force. And that is our adaptive mechanism, because we are going for running, we might go for a fall, we might go for a jump. These are all fast activities, and fast and rapid loading are there in our human body, and we are able to withstand that. That is because of this property of the bond, which is the strain rate of the bond. The bond is having a greater amount of force to resist, or bond better reacts, you can say it like that, bond better reacts when the force is fast loading. So bond is a viscoelastic substance, or it has a viscoelastic property where when it is loaded in a fast manner, when it is fast loaded, it responds better to that, It leads to hypertrophy of bond, and bond growth. We studied that. Bond growth. Wolff's law, which says that for structure of the for bond depends upon the function or the load that it has been, or the stress that it is being able to, it is subjected to. Okay, and that is what we have to see in the strain rate, which says that fast loading is better for the bonds and slow loading is not that good for the bond, right? So this is the general properties of the bond which we were able to discuss, and this property is unique for the bond, whereas the other substance, steel and other substance, are not better reacting to fast loading, or the wood or any other substance, but the biological structures are having this unique property, and that differentiate from ceramic and other PMMA etc., which we use in bond grafts and joint replacements etc. And now to summarize, we see that we have cortical and cancellous bond. The cortical bond is having better stiffness, or it is having a greater amount of stiffness than the cancellous one, because you know that. This tough one, this is just weak one, which is having soft cavities, which is having trabecular system. But the cortical bond responds better to stress. But when it is to strain, change in length, this bond is going to be weak, because it cannot resist change in length. And here your cancellous bond, which is lower in this side, is going to come up, because it is able to withstand greater amount of strain change in length, because you know that it's a trabecular system, it has free filled cavities, so it can resist about a great amount of force. So stress is more better in the cortical bone, strain is more better in the cancellous bone. And that is why when you have an increased strain at those areas, you have increased deposition of your cancellous bone and the trabecular system, especially in the neck of the femur, etc. Right? These are the general properties of our bone, general mechanical properties. And this mechanical property shows changes as we ages. We go to the pathomechanics. One of the pathomechanics is aspect is that when the age progresses, the mechanical properties of the bone comes down. The Young's modulus of it comes down. After 35 years, the Poisson's ratio comes down. The fracture toughness of the bone comes down. The strain rate sensitivity of the bone comes down when the patient goes for age. And that has an application how. That is why, one of the reasons why elderly has a frequent falls and fractures are more common in elderly, especially the neck of the femur fracture are more commonly seen after the age of 60. That is maybe one of the reasons for that, right? So this is one of the application. And second one is that bone is able to resist, or bone is able to perform best when there is some loading. When there is less loading, when there is less stress, or when there is less compressive force, the ability of the bone to grow is actually decreased. And that is one of the application. In few years back or a few decades back, when there was osteoporosis, what the people used to say, need not walk, no need to walk, you have osteoporosis. But now the scenario is different. We have to walk because that will only help in the circulation, that will only help in the diffusion, that will only help the bone to be strong, bone to increase its bone mineral density, otherwise it will decrease. That means the bone mineral density decreases when there is less loading. And osteoporosis is a decrease in the bone mineral density. So the application one is that in elderly, the viscoelastic property and all the properties is going to decrease, especially after 35 years. When there is a rapid loading, bone able to withstand more. When there is a slow loading and no loading at all, bone can decrease its bone mineral density, and it happens in osteoporosis. And when there is a decreased loading, like in space travels or in space station, the gravity is less and bone loading is less, there can be weakness of the bone. So bone is a magnificent connective tissue. It's a magnificent structure made up of collagen and hydroxyapatite. It is having some unique property which differentiate it from other structures. And this unique property, along with that bone's characters, provide the stability, rigidity, and protection to the human body, as well as help in withstanding or dissipating force. Earlier we discussed the mechanical properties, which first one was anisotropicity, fracture toughness, ultimate strength, and strain rate. The first one was actually anisotropicity, and there we saw two constants. One is E, Young's modulus, and Poisson's ratio, which is actually, I forgot to mention, that is lateral strain by lateral stress. Lateral strain by lateral stress. Lateral strain by lateral stress. The Poisson's ratio is actually lateral strain by lateral stress, and it has a value of 0.15 to 0.43, but we take a value of 0.3 for the reference. So the Poisson's value for our bone or the cortical bone is 0.3, just remember that. And the formula for discovering Poisson's ratio is lateral strain by lateral stress. So this is a summary of the mechanical property and biomechanics of bone. If there is a question about biomechanics of bone, you have to define what is bone, you have to define what is the function of the bone. Then you go to define what are the characteristics, what are the organization of bone, structure of the bone, two collagen and hydroxyapatite, the cellular components in the bone, two types of bone, and wound and lamellar bone. Finish go for the mechanical properties. Just define what are the mechanical properties, define what is Wolff's law, then go into deep. The mechanical properties, anisotropicity, fracture toughness, strength, and strain rate sensitivity. These are the mechanical properties of the bone. Summarize there. Go for the pathomechanics, wherein changes in elderly, changes in osteoporosis, changes in microgravity environment. Just mention that. That's complete. And just summarize it. That's all. And then bone also exhibit one more property that is known as creep. What do you mean by that? When the bone is repeatedly loaded and unloaded. That means when bone is loaded, unloaded. Bone loaded, unloaded. The properties of the bone will change. the properties of bond will be lost. So repeated loading and unloading is not good for the bond. Continuous and repeated loading and unloading is not good for the bond. That is known as creep strain of the bond. That is another property. Only if you want, you just remember. Otherwise, just leave it at and well good with these things. That's all about this video on biomechanics of the bond. If you like the video, don't forget to click the like button and subscribe my channel.